practice this.
Amy.
Somebody else get a copy of that practice test? Oh, you good?
So, guys, so trig functions themselves, I want you to get this idea. Trig functions themselves are defined very strangely, if you think about it. A trig function, how is a trig function defined? Any trig function you have, how's it defined? How's cotangent defined? How's sine defined? So don't be specific. What are they basically? So let's be specific. What's sine of an angle? The ratio. I like that word. Of? Scared of it. Shit.
The opposite of hypotenuse.
Sure, if you like SOHCAHTOA, I like it. So it's the ratio of the y side to the hypotenuse, or opposite of right line. I like it. You guys kind of with me? So basically, when I said what are all trig functions defined as, ratios of sides of right triangles, right? Which is really a weird way to define a function. We've never done it like that before. I don't even know if you guys, I'm not trying to make trig functions seem weird now, but that is the truth. So there's more to the story than this, but I just don't have time to get into it. But this is, it's given that that function, like a sine, because you can actually look at taking hyperbolic functions and defining ratios of sides of something based on those hyperbolic functions, just like we had for a circle. So that's why they're called hyperbolic trig functions, because they're based on hyperbolas, not circles. All right. So that's. But another reason we give them the symbol is also because of the way they interact with each other. So this is a way, and the way you say this cinch. You can even put a C there if you want to make it into an actual English word. Cinch. So how would you say this?
Cosinch.
No, come on. That's too long. Math people, we... Coach. Coach. And then this will be... Tanch. Right? That sounds... I don't know what that sounds so weird. That has fried tanch. I don't know. Sounds horrible, actually. And what this is, for example, the cinch, well, I always forget it was a minus or a plus. That's a minus. The cinch is defined to be that. So if I had to do derivatives, that would be relatively easy. Hopefully you guys agree, right? And the cosh is defined to be this. So what would the tanch be? What should it be if this is a decent and good world that we live in? Say again? Yeah, cinch over cosh. And what would that become?
Ex minus E minus X.
Because the 2's would cancel. Is that cool? All right. Yes, sir.
For the cinch, is it e to the y or is that e to the x? Minus.
It's all e to the x. It's all x. Yeah. It's a function of x. I like it. So take a second or several and do the derivative of cinch. Do the derivative of cinch. Figure out what that is. Don't guess at it because you'll be wrong. You can always simplify the function you're working with before you take derivatives. So it'd be easier to kind of pull that apart, make it look like two separate terms. Yeah. So what do you get? Derivative of 1/2 e to x is 1/2 e to the x. So derivative of 1/2 e to the negative x. 1/2 e to the negative x times. So it'll be minus 1/2 e negative x times the derivative of negative x, which is negative 1. The inside function is not x. The inside function is negative x. Therefore, chain rule will show up. How we doing? Which, like John said, what is that? That's cosh. So do they act the same way as the circularly defined trig functions in terms of derivatives? Already they don't. Or they do so far. I mean, if you do cosh, now do the derivative of cosh, what's going to happen? It would become sinh. So there you would see that cosh derivative is actually equal to sinh. There's no negative involved in the derivatives. How are we doing so far? Alright, that's jumped the gun there a little bit, but that's where you start to see that they're not exactly the same. I like it. And somebody help me out. Alright, let me see if you guys understand this. This section for me is sort of, hey, these exist, guys. Yeah.
Is this 311?
This is 311. Yeah. This section for me is a hey, these exist. These are going to show up. Sometimes it's the best way to write the answer to something. It's a more concise way to consolidate a bunch of e to this stuff running around inside of a problem. Right? So they exist. These exist. They have certain properties, so like any function would. I'm not going to make you memorize basically anything to do with these. I want you to do the homework so you know these exist. Because if you go further in calculus, they're suddenly going to become a little more important. Right? But right now, I just want you to know these exist. But remind me, what's the equation of a circle? Any circle? Let's say centered at the origin, just make it nice. What's the equation of any circle centered at the origin? And if you divide by r squared, I'm sure you guys have seen this at one point or another, x over r is, of course, what's x over r? Cosine. I love it. So that's where sine squared plus cosine squared equals 1. That's another way to get there very quickly.
Oh, snap.
Snap is right. Holy shit.
That just happened.
Alright, let me stop there for a second. So here's what's really cool. What is the difference between the equation of a circle and the equation of a hyperbola? The main difference.
Circle is complete.
The difference, and what's the difference between the equation of an ellipse and the equation of hyperbola? Who remembers? There's one big glaring difference. An ellipse equation is...
What's a hyperbola?
Alright. What's up? Not really. A little bit, but not really. An ellipse would have different numbers here possibly, right? But it's still basically the same formula. It would just have different numbers here because it's differently shaped in the x or the y direction. You with me? Why is this one a circle? Because in both directions it's got the same adjustment, right? So it's circular then. It's symmetric in all directions. So I'm not talking about that. I'm talking about what is the main difference between this equation and the equation for the related hyperbola. I would just take the plus and make it a minus. You guys remember that? No.
I said that.
I didn't hear you. Sorry, Kevin. Okay, speak up. So if that's true, this is why it makes sense that for normal trig functions, sine squared plus cosine squared equals 1. For hyperbolic trig functions, cos squared minus sin squared equals 1. Because of what they're based on. These are hyperbolic are based on hyperbola, so therefore the minus in there makes sense. Normal trig functions based on circles. That's why the plus in there makes sense. I just want to point that out. That's where this comes from. Okay, maybe. All right, so any questions on that? I mean, you've got time on that homework. I'd much rather you focus on the homework through 310 for right now. This homework is going to be relatively easy. You don't have to memorize anything. You just have to use it. Let me give you the answer key for the practice test, and then I'll see if anybody has questions from that.
They thought you did better than 10.
Yeah, no, you're right. This is your base.
And also, somebody came by my office earlier and reminded me of this, and I think I said this earlier this semester, but you guys have so many resources available to you now. I am one person. What am I trying to get at here? I say things and look at things a certain way. As a teacher, I try to look at things in several different ways. So I don't know if you picked up, but sometimes I'll say the same thing in a few different ways. Because I'm trying to say it the way it's going to click in your head. There's no way in hell I can think of every possible way to say everything. So that's why it's important. Go find a YouTube channel. Go find another textbook besides the textbook that we picked. That's what I did when I was going through college. I got a hold of some other textbooks and stuff and said, oh, this guy makes sense in this section, but this makes sense in this section, and he actually makes sense in this section, and you try to piece it together. As a student, this is what you do. My textbook, me, my videos, that's one resource. How many resources do you actually have? The crazy on it. The tutors in my study center, all this stuff, right? So if you feel like you're supposed to get all this stuff just by coming to class and then doing the homework by yourself, you're a little insane. I want to save you from that, right? You're a little insane. Now you're just going to drive yourself more insane, right? And then you're scary. I don't know what you're going to do. Yes?
So for 3F, you wouldn't go like the full 8 hours forward and then like 7.5 back?
Where am I at? 3.
F?
F. No. So what I say, I should have said the position. No, I just asked how fast is the train going a half hour. So I didn't really ask that question. That gets weird. That you still have to do for the homework. What's the total distance I've gone? Then I would have to be careful about where I turn around.
Right.
Kind of with me?
Yeah.
But this just asked me how fast was I going half an hour before I got back. So I just got to figure out when do I get back, and then take half an hour from that. Yeah, do you guys see? I love that kind of question. So expect that kind of question. I'm going to ask you, where are you 20 minutes before your acceleration is -30? And you're like, what the? I don't know, shit.
Well, I just did it both ways. I didn't know which way you were asking for.
Yeah, I personally don't like that question. What's the total distance you've actually gone? There are other ways to calculate that, but they have some in the homework like that. That question was more direct. I didn't really finish number 5 because I sort of ran out of room there. I didn't even have time to check, so hopefully it's right. Let's see. Number 5 is the one related to the linear approximations. So the function I give you there is that natural log. So if it helps you, you can either remember this, which you all already know because it's just y equals y1 plus m times x minus x1. That's what that is. Right, y minus y1, I just added the y1 over, equals m times x minus x1. We know, you should know that formula, right? That's, if you notice, that's all this thing is. M is the derivative, a is x1, so forth. Same thing. So if it helps, you just look at this kind of problem and say, let me find the tangent line at that point. Okay, and we've done that kind of problem. That's exactly what this is, just find the tangent line at that point. The real new part of this section is, how long does that line give me decent enough answers so that they're not too far away from what the actual function answers would be? So what do I need to figure out for this?
At the point.
Alright, so I need to know what f of -2 is. What's f of -2? -2 or 2? Hopefully 2.
-2.
Is it it's plus 3. There you go. Something going on. So -2 plus 3. What's the natural log of 1?
0.
0. Cool. So I know I got the point. -2, 0 has to be on my tangent line. My linear approximation is what we can call it now. And what else do I need to force? Derivative, so I can figure out what n is, the slope. So what's f prime? Kick ass, so f prime at 2, at negative 2, it's 1. I like it. So what's that equation? And here's how I do it. I just say y equals 1x. Alright, if I plug a negative 2 in, it's supposed to be 0. So when I plug a negative 2 in, what do I do to negative 2 to make it 0? I add 2. There you go. So I don't mess around with b shit and y minus y1 shit. Just start writing it down and make it work at the end. If you don't like that, you can use the b shit or the y minus y1 shit. It's alright. Stop there for now. If you just plug it in, what do you get? You get f of x is approximately, so natural log of x plus 3 is approximately f of negative 2 is negative 2 plus, is that right? F of negative 2 is 0. You do it, Jeff. Plus f prime, which was 1, times x minus a, which is negative 2. I'll get there eventually. So that is approximately x plus 2. There you go. That took a while just to get to the same place. So to be honest, I understand why we write this, because when you get to 280, you're going to add some more terms on here related to like the second derivative and the third derivative and the 8 billionth derivative. You're going to have basically a series that's going to go forever. And the further out you go, the better your approximation is, because then you're matching the curvature and all that kind of stuff. And just instead of just matching the slope, you're going to match more things. Let me stop there for a second. You guys kind of get a feel for that? So I agree with this. At the same time, this is all I'm doing here, really. It's just getting the equation of the tangent line. That's really all that does. So if you can do that, do it. And you'll end up doing that. So how do I do the next piece of this? It says, use what you find to approximate natural log of 1.03. And what do you have to be careful about? What's x?
Oh, it's a point.
Negative.
Yeah, what you can do is, you want x plus 3 to be this. So then subtract 3 and you get negative 1.97. Kick ass. You stop there for a second. So be real careful. If the function you're working with has more than just x in it, what they ask you for can't be just x. It actually is whatever that is. And you can solve for x. So then how do I use what I found to approximate the value at this point? I just plug that in. So I get y equals negative 1.97. Let me say that this. Sorry. F of negative 1.97, which is the natural log of 1.03, is approximately negative 1.97 plus 2. Okay. Which is, of course, 0.03. Oh yeah, I think I did check it. In the natural log, has anybody done that? What is the natural log of 1.03 actually equal to? Use your calculator.
0.295.
Oh.
0.0295.
0.029. 6, I think, if you round it to that place. But yeah, I like it. Seems like, come on, man. It's good enough. Forget about work. And that is basically that, and that's pretty damn close. It depends on what close means, though, right? So this could be very far away for some people. For me, that's pretty damn close. So who remembers how to, if I ask you to be correct to within 0.01, yes, sir?
So you set x plus 2 less than or equal to the ln x plus 3 minus 0.01, and then the ln x plus 3 plus 0.01.
Yeah, so I want the function minus 0.01. So I want to have all the outputs that are 0.01 away from the actual function. In the middle, I'm going to put my, so this is going to be y1. y2 is going to be my approximation. And y3 is going to be the ceiling. So floor, my function, ceiling, and then I want to see when do I hit the floor or the ceiling. I want to stay in the room, right? I don't want this thing to bust through the ceiling or, bless you, dig through the floor.
It's a wild card.
Huh?
Wild card.
Wild card, exactly. Natural logs, they go insane. Let's see, we'll turn this bad boy on. Any questions about that, what we've done so far? You're going to have to be able to do this on Wednesday. So if you have a calculator and you want to play along, see what happens. Let's see, sorry, right, just a second, yeah. So if I want to be within 0.01, that's the lowest I want my function to get, right? That's within 0.01 that way. Put my function in the middle. Get in there. And then I've got ln x plus 3 plus 0.01. Alright. Now, of course, my first graph is going to be horrible, but we'll make it better. Alright, mouse. So if I hit zoom 6, that's the standard window. There's the ln. There's my function, and there's everything's happening right here, of course, because that's the point is -2. So that's why I love zoom box, because to be very, very specific, you have to play around with the window. Playing around with the window gets kind of annoying. So everything's happening right there. So I want to zoom in there. All right, there's the floor. There's my function. Ooh. And there's the ceiling. Yeah. So I can see I need to zoom in a little more. Is that cool? Yeah, you just keep doing this until you can see well enough. So things get kind of pulled apart. Yeah, you can stay here, Jeff. Alright, so enter. Oh my god, this is so exciting. Probably have to do more. Let's see. Ah, I can see a little bit of separation there. Thank God. All right. But I mean, I really want to just force us to go through this so you see what's involved. I think when I first showed you this, I tried it. Let me see what I can do here. So we know it's all around this 2. Let's see if this is too far. This might be too far. Gone too far. Yeah, this is too far. Shoot. Yeah, it's too far. Too far for Jeff. But do you see what I'm saying though? Do you see why it's too far? I don't see where it's hitting the floor anymore. I knew it was hitting the floor earlier. So anyway, so I could, if I zoom out, it's going to suck. Oh well, too bad, Jeff. Probably right back to where I was. Excitement is palpable.
I can't continue.
I like it. I think it's actually crossing through here, right? Almost a little bit. Yeah?
Yeah, totally.
No, watch. Let me do this. I think it's the ceiling it's hitting. Let's just graph the function and the ceiling. Yeah. I don't know if you can see it. See how the ceiling's above it and then it's below it? So like if I wanted to, right there, let me see. I can find this edge of it. This is not exciting. I don't give a shit. This is what you got to do. I might be the only one excited right now. All right. Oh, dude, it's up here. Oh, all right. Anyway. So, thankfully, on the actual test, I'm going to give you a little bit of a wider range. You have to be as freaky as me, right? So you can see the separation. But what was I looking for? I was looking to see the separation so I can actually see which side is my function, my estimation, hitting. And the whole thing is to find those intercepts between my estimation and the ceiling or the floor, whichever one that it actually hits. Because then it's outside the room. I want to stay in the room. You guys kind of... Yes. All right, any other questions before we head out of here? I mean, tomorrow we're going to review more. So if you haven't had a chance to do this yet, you got till tomorrow.
Related rates tomorrow?
Of course.
Of course.
So tomorrow, bring your specific related rates questions, whatever other questions, and we'll just focus on that next tomorrow. Yeah. Yes, I would highly prefer that.
Can I have one of those?